Hello, everyone. I would like to present you our work on how a deeper understanding of theoretical data movement can lead to the development of better practical algorithms for distributed linear algebra kernels, for example, matrix factorizations. In this presentation, I would like to focus on two main contributions of our paper. First one is a theoretical one. We establish new parallel I/O lower bounds for Cholesky and LU factorizations as a function of matrix size of the fast memory, for example, private cache, and number of parallel processors. And later on, we will discuss how these insights can lead to the implementations that compare against state-of-the-art libraries, not only measurably communicate least, but also can significantly reduce the total time to solution. Okay, so let me start with a short motivation. When I say matrix factorizations, then maybe some of you may think of LU factorization, and if LU, then maybe LINPACK benchmark, and if LINPACK, then probably top 500. So indeed, actually, we used LU factorization to rank top supercomputers worldwide for decades. And here in this business, we of course have all the big hardware vendors, and speeding up LU factorization is of high interest of both commercial library vendors as well as spawns a lot of interest in research community. But of course, LU factorization is not about LINPACK benchmark, but because it is ubiquitous in many fields of numerical sciences. But of course, matrix factorization is not only LU. For example, Cholesky factorization is very popular if the input matrices are symmetric positive defined, for example, in quantum simulations where the symmetry exploits natural symmetries of simulated quantum systems. So again, improving performance of Cholesky factorization and spawns a lot of interest in scientific community for decades already. So then the question is, what new insights can we develop for this, well, old and already highly optimized kernels? Well, in this work, we take the approach of optimizing for data movement, because currently for high performance computing, we can say that in general, the less data movement, the better the performance. So we start by establishing new general method to derive tight parallel I/O lower bounds for general class of programs, and then we will use this mathematical framework and we will apply it to matrix factorizations to obtain our new practical implementations. So we will start with an input program. For example, here we see a LU factorization without pivoting, and we will model the execution of such program as a computational directed acyclic graph, where every vertex represents some elementary computation and edges represent data dependencies. So on such a CDAX, we will establish a class of programs, general class of programs, for which we can precisely model data movements here. So this will be our DAP, disjoint array access programs. So if the input program is of DAP class, then we will be able not only to establish tight I/O lower bounds, but actually derive corresponding I/O optimal sequential schedules. So on this DAP, on these CDAX, we will design a certain optimization problem, and the solution to this optimization problem will actually yield our I/O optimal sequential schedule. But more on it later. Now the key takeaway is that because this proof is constructive, when we apply it to matrix factorizations, not only we get new parallel I/O lower bounds for LU and Cholesky, but also we can use it to derive new distributed schemes for these factorizations, which minimize communication not only across the memory hierarchy, but also communication between parallel processors. Now, combining this communication avoiding schedules with a series of performance optimizations, for example, local data layout transformations and optimized class calls, we get the final result that communicates up to 1.6 times less than compared to state-of-the-art libraries, and can decrease the total time to solution up to 3 times. Finally, I want to mention that these implementations are fully ScaLAPACK layout compatible and are available as open source libraries. So these can be used just as plugin for applications that already use LU or Cholesky factorizations. Okay, so let's start with the first one, this general method for deriving I/O lower bounds. So how can we get from this input program to our tight I/O lower bounds and sequential schedules? Well, so let's start with defining this DAP, disjoint array access programs. So here we have an example of that. So what we have here, we have some arbitrary loopness. These loop ranges may depend on outer ranges. For example, here this range goes to I. We have the input, which are some multi-dimensional arrays, and we have the output, which is also an array. So this may remind you of, for example, polyhedral analysis or this classic formulation of arrays in loops formulation. But here we actually extend polyhedral model. So we allow any injective functions here. So we don't rely on affine accesses here. And also the iteration domain can be any countable set. So we can model iteration domains which are exponential or logarithmic, for example, here. We have also 2 additional assumptions. First assumption is that different arrays are disjoint. There is no aliasing between such arrays. And also multiple accesses to the same array are also disjoint. So this is the defining property of DAP. Now, what do I mean here that different accesses to the same array are disjoint? Well, if I show you this array, input array A, then what I mean here is that any element of this array is accessed either by one access function or the other. So we don't have this ambiguity that one element can be accessed from different access function vectors. Okay, so if the input program can be represented with these constraints, now we can proceed to establish our tight I/O lower bounds. So how to do it? I want to show you the intuition behind our key lemma here. So here we have an example of that program. So the main idea is we want to reason how many useful computations can we perform for a given number of I/O operations. So we want to do the computations as cheaply, as I/O cheaply as possible. So the geometric intuition may be that this iteration space will be some multi-dimensional lattice, computations will be volume, I/O would be surface, and then the objective would be to maximize this ratio. This may sound a bit complicated, but let me show you the geometric intuition here. So we have our 3 loops, I, J, K, and the input arrays, for example, array A lives in this IJ plane here, array B would be here, and array C will be here. And now the output array, this array E, will form this 3D iteration space here. So what it means that every vertex in this lattice corresponds to a unique evaluation of this statement for a fixed I, J, and K. Okay, so now for a computation. So let's say that we want to compute some part of this iteration space. So now the question is, what is the minimum I/O requirement to perform these 4 computations? And now this I/O would be the surface, so this will be the projection of this set here into this input arrays A, B, and C. So here, if we just put that as a parameter, this how many different values iteration variables I, J, and K take during this computation, noting this DI, DJ, and DK, well, we can think of intuitively as this per computation are these local domains, so can think of it as tile sizes for this optimal computation. So for each computation, we want to find this optimal tile size that minimizes the I/O movement, and then formulating it as an optimization problem, we want to maximize this volume subject to the constraint on the I/O, so on this surface here. Now, proving that this is actually optimal and covering all narrow corner cases actually requires quite a tedious mathematical work to consider all the cases, but you can find all the details in the paper. Now, I want to emphasize why actually do we need this whole DAP? Why did we introduce this new computational model in the first place? Cannot we use the existing tools? Well, the important thing is that because we have this disjoint array accesses, here we can use addition here. So we can add the sizes of these sets. So if we don't have any assumption on this overlap, then basically all we could do is just take the union of these sets, and then we can bound it only with the max function. And this will generate the I/O bound, which is not tight. And this is very important because tightness of the lower bound implies the existence of corresponding optimal schedule. But if the bounds are not tight, we don't have any information how I/O optimal schedule would look like. So DAP not only gives the bound, but from this tightness gives the corresponding tiling and schedule. Also here I want to mention that because we are dealing with arbitrary set sizes, here we are not relying on polyhedral analysis, so we can have exponential or logarithmic iteration sizes. Okay, so this is the general intuition behind our general method. Now let's see what happens if we adapt this methodology to matrix factorizations. So matrix factorizations are perfect candidates for our DAP model. Here we have LU factorization. I omitted pivoting for brevity, but we'll get back to pivoting in a second. So what we have here, we have two statements, S1 on green, so this updates a leading column, and S2 on blue, that updates a shorts component. We already see an interesting data movement pattern. For example, observe that here the output of the first statement is the input of the second statement, posing possibility for data reuse between statements. So this is also captured in a DAP model, so we can capture a data flow between statements. Okay, so the CDAC of this computation will look something like this, with blue vertices correspond to elements that are computed by the statement S2, and green vertices corresponding to statement S1. So on this CDAC, we formulate our DAP optimization problem, so maximizing this volume for the constraint on the I/O on the surface here. So solving this optimization problem, we obtain our I/O lower bound for Cholesky and LU, and we get our optimal schedule. So here is Ti and Tj are I/O optimal tile sizes in I and j dimension, and this is square root of the size of the fast memory. So how would such I/O optimal schedule look like? Well, if we want to factorize, for example, this matrix, then what we need to do is first compute this top left corner, then we update this leading column, then we update this leading row, and then what we do, we load square root of S elements from this leading row and leading column. We store in a fast memory S partial outer products here of this reduction, and then we stream through these elements and updating the S outer products that are in our fast memory. So this probably maximizes the data reuse and minimizes this data movement across the memory hierarchy. Okay, so now the question is, how can we design a parallel schedule for it? And the interesting thing is that this is actually not that obvious. Well, what is the problem with parallel schedule? The problem are loop carry dependencies. So if we take a look at this CDAC and we extract this top left corner, leading row, leading column, and source component. And what we see is that actually only in this last part, the source component, we have only commutative dependencies only. So we can use a provably IO optimal 2.5 deparallelization. But for the remaining parts, we have this loop carried non-commutative dependency. So we cannot parallelize in the reduction dimension, which will invalidate our IO lower bound. So here we need to do something clever here. How can we reduce the communication for these three parts? So let's take a look. How can we do it? Introducing conflux and conflux, our communication avoiding distributed factorizations. So let's say that we want to factorize this 16 by 16 matrix using 8 parallel processors. So let's bring the matrix to the middle here, and let's color code our processor. So the color will correspond to the owner of this data in this distributed fashion. Okay, so now let's extract our top left corner, leading row, leading column, and source component. We start by replicating A00 to all processors. So here we redundantly, every processor computes this A00 without any latency cost. Now for these parts, we have non-commutative dependencies. So we do one deparallelization. So we parallelize only either across rows or across columns, like this. And then finally, for the remaining parts, because we have only commutative dependencies, we can use 2.5 deparallelization. So we will parallelize both across rows, across columns, and we also parallelize across reduction dimension here, which minimizes communication between the ranks. Now observe also that this key parameter here is the square root of s. So the defining property of this schedule is this IO optimal sequential schedule. So this is the size of this individual tiles. So this schedule not only minimizes communication between ranks, but also each rank minimizes communication locally across its own memory hierarchy. Okay, so now, of course, this matrix factorization is an iterative process. So in the next step, these elements will form our leading column. So we need to reduce them. So let's add column reduction here. And for LU, we need to perform pivoting. So we use here a tournament pivoting strategy. Why? Because so the important feature of the tournament pivoting is that in, let's say, one go, it can compute square root of s new pivots that is needed for our 2.5 deparallelization of A11. It was shown that tournament pivoting is as stable as partial pivoting, and it reduces latency and provides our chunk of square root of s new pivots here. But you can find all the details of this scheme in the paper. Now, after the tournament pivoting, we need to distribute this data to our 1D and replicating scheme. We also need to reduce our pivot rows and scatter this data to A01. And this is more or less the sketch of our communication avoiding distributed matrix factorizations. Okay, so now let's see how much this data movement reduction actually buys us in terms of performance. So let's go to the evaluation. So we compared our implementations against Intel MKL, SLATE, and CANDMC and CAPITAL. So the last two, CANDMC and CAPITAL, use asymptotically optimal 2.5 deparallelization, but actually constant terms are pretty high, and it will significantly actually increase the communication for small number of processors, as we will see in a minute. Intel MKL and SLATE use 2D parallelization here. We tested it on the CSCS Piz Daint supercomputer using up to 512 compute nodes connected via Dragonfly topology, and we measured both time and total communication volume. As for the problem sizes, we really wanted to cover the whole spectrum of matrix sizes here. Well, why? Well, because, for example, Piz Daint for LinPack benchmark uses matrices with more than 16 million rows to get as close to the peak hardware performance as possible. But clearly, such huge, dense matrices are almost never factorized in practice. So the largest matrices that we observed in practice were in density functional theory, and there were up to 130,000 rows. But for example, one of the important use cases in our work in second order neural networks, in the backpropagation, we invert Kronecker factors, and here the number of rows is around 4,000. So we wanted to have high performance both for small and for large matrices. Okay, so let's first take a look at communication volume. Here I want to show you the communication volume per rank as a function of number of ranks. Note here the logarithmic scales. And we will start with strong scaling. So for n equals 16,000 rows, just to put in a perspective, if we use one MPI rank per node, this would be the sizes of the Piz Daint, Summit, and Taihu Lite supercomputers. So these are the results that we measured here, with conflux being this violet cross. And here we already measured 1.6 times communication reductions. But also the important thing is that we established analytical communication models for all these implementations by going step by step how the algorithms perform their tasks. And by extrapolating these analytical models, we would expect here more than 2 times communication reduction, for example, for the Summit full run here, extrapolating these models. And we see similar trends not only for strong scaling. If we plot also weak scaling here, we see that conflux communicates constant as for each MPI rank here, and asymptotically not optimal CANDMC and SLATE that use 2D communication will increase this communication as we scale number of ranks here. Now, showing these results as a heat map, here I want to show you the communication volume reduction versus second best library. M will be for MKL, S for SLATE, and C for CANDMC. For each combination of number of ranks and matrix sizes. Here we see this trend. So here on the top left corner this is up to what sizes we measured it. So we, as I mentioned, we measured up to 1.6 times communication reduction. Now, by extrapolating these models, we can expect significant communication reduction even for larger matrices and now larger number of ranks. Okay, so how this communication reduction actually translates to performance. Let's take a look here. So here I want to show you the percentage of peak machine performance for LU factorization. So this will be a plot of peak performance achieved as a function of number of nodes. And this will be both for strong scaling for large matrices, strong scaling for small matrices, and for weak scaling. Here what we can see is that conflux, here on violet, significantly outperforms other state-of-the-art libraries, especially for these cases on the left of this plot. So this is where all these implementations achieve relatively high machine utilization. So these are the scenarios that probably are most practical. Well, we don't want to underutilize these machines. And in this regime, actually, we see significant improvement in the performance. And we see similar trends for Cholesky factorization too. So here again, we see significant speed ups for ConfChocs, our Cholesky factorization, compared to the remaining libraries, both for strong and weak scale. Now, showing these results, again as a heat map. So this will be the speed up versus second fastest or competitor. Again, M will be for MKL, S for SLATE, and C for CANDMC and CAPITAL. For LU factorization, observe that here for any combination of matrix size and number of nodes, we see an improvement of performance, except of these rare cases on a very, very right. But here, anyway, the machine utilization is very low. So these scenarios are probably not very practical to launch. And here, for example, for an important use case for us, we see up to 3 times better time to solution compared to the second best, which was SLATE. And we see the similar trend for Cholesky factorization here. So again, we see the biggest speed up for small matrices. And for example, here in this case, we see up to 1.8 times faster. And the second best is MKL. Okay, so to conclude, in this work, we introduce the general framework for deriving tight parallel I/O lower bounds and corresponding sequential schedules. And then we applied our modeling to matrix factorizations, and we established new parallel I/O lower bounds and also a new communication avoiding parallel schedules. And combined with our implementation optimizations, we reduce total communication volume and time to solution compared to the state-of-the-art libraries. You can find the implementation of our matrix factorizations. They are available open source on GitHub. Thank you very much for your attention.